Good morning, everybody. The first speaker of today is Professor Garoufalidis from Georgia Institute of Technology, who will speak about asymptotics.
Okay. So my name. Which alphabet is this? Is Garoufalidis, and as you can tell, the cultural relations between Russia and Greece, the country I come from, run many centuries deep. I would like to thank the organizers for the conference for giving me the opportunity to speak to this occasion, and it is the first time of me in Russia, a country I've heard a lot about. It is wonderful to see that there are many Russians in Russia other than the ones that I have met in the diaspora, meaning outside Russia. I would also like to thank a lot the graduate students who have helped in so many ways and have solved all problems, you know, the most trivial or the more difficult ones, and have made this conference really a wonderful place for all of us. I'm really impressed and thankful. Okay. And I would also like to thank the organizers, Vladimir Duraev and Sergei Matveev, for dealing with, I'm sure, volumes of paperwork to make this conference happen.
As long as you're established, is there anything you can take me?
Yes, later. All right, so I want to talk about asymptotics, and this is actually joint work with Don Zagier. It's work that started about 6 years ago. We still do not have a manuscript, but we have 3 papers in preparation, in various stages of preparation. And I will talk about concrete numbers. I will not talk about groups, abelian groups, fundamental groups, homomorphisms, categories, and other things like that. I will try to talk a little concretely, so let me start with some numbers and their theory, otherwise known as number theory. So I will start by choosing a number. By complete accident, Sergei Duzin chose the same number. So I will remind you that alpha is a root of the polynomial x cubed minus x squared plus 1 equals 0.
In my case, it was minus 1.
It doesn't matter. You replace alpha by 1 over alpha. But it will not matter. But of course, a cubic polynomial has 3 roots. So which root do I mean? Because I'm talking about a concrete number, right? So out of the 3, I select this one. Right? Of course, there are many dots here because this is an algebraic number, but irrational. Therefore, I mean, I can, you know, I cannot give you the entire digit expansion. But it is, in fact, something called an algebraic number, in fact an algebraic integer. Why is integer? Because it satisfies a polynomial equation with integer coefficients, and the leading coefficient is 1. So that's a monic equation. So those numbers are actually integers. Secretly, that number has to do with two knots, which I will draw for you. This is 1, 3, 1, 2, 3, 4, 5, 6, 7. They are not braids, but they are knots. This is the -237 pretzel knot, and this is the 5-2 knot. So secretly, this number has something to do with these two knots. I will tell you in a little bit what this means. So a number alpha generates then a number field F, which is all rational functions of alpha, which is the same as all polynomials of alpha modulo the defining relation, as we all know, right? So in particular, so here is an example, a concrete example, 1/3 plus 5 alpha. Is this clear that this is a complex number? Not an element of the field, an abstract field, but a complex number. This is a complex number, right?
Yes.
Okay, good. So it is 1/53 of -24 plus 40 alpha minus 25 alpha squared. So every element in this field can be written as a polynomial in alpha with rational coefficients of degree at most 2, canonically, uniquely. That is called exact arithmetic. That's what algebraic numbers are. Okay. Now, because I actually told you a specific root of that polynomial, this field F is not an abstract field, but in fact a subfield of the complex numbers, a subset of the complex numbers. So every expression like that is not just in that abstract field, but in fact it is an explicit complex number. Okay. There is an alternative expression for alpha, which I will start writing only a few pieces of it. So the alternative expression says this. One-third plus blah, 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 blah. What is this alternative expression? Well, the solution to a cubic equation with rational coefficients was done in the Middle Ages, and this is the solution to it. It involves square roots and cubic roots. You may have seen it in advanced courses, but this is useless. That's not how I want to think of alpha and other things that I will later on construct. Okay? So, okay, for a cubic equation, yes, you have such an expression which takes so long to write, but these are much more compact expressions and convey the true meaning of alpha. And if it was a cubic equation, as we also know, it would not be possible to do that at all. So, okay, so F is a number field, a concrete number field, and it has a discriminant of the number field F. What is the discriminant? It is, if you have a polynomial, the discriminant is a number that you get out of its coefficients, that number tells you which roots of the polynomial collide. But of course, this polynomial has three complex roots, and they don't collide. But the discriminant does tell you something. The discriminant of this number field is minus 23, which tells you the following thing. So here are the primes, which are the integers of the rational numbers. Sorry, these are the integers, which are the algebraic integers of Q. And among those integers, you know, there is 5 or there is 7. 7 is a prime. And 7 in that number field F splits into a product of 3 prime, really prime ideals. So most primes here split into products of 3, except finitely many primes, and it's important that it's finitely many. So there is this 3-to-1 kind of covering which is ramified. So there are some unlucky primes. And what is the unlucky primes for the specific number field? They are exactly the ones who divide the discriminant. Do we all agree that minus 23 is a prime number?
Yes. No. Yes.
Because don't worry that it is a negative. A prime number is an integer whose divisors are it up to units, and there are 2 units, namely plus or minus 1. So minus 23 is a prime number. You don't normally teach that, but minus 23 actually splits in this way. So let me define pi 1 and pi 2 for you. So I claim, so here is a little lemma, that minus 23, I'm not talking about ideals, I'm still talking about numbers. Minus 23 is pi 1 squared times pi 2, where pi 1 is equal to 3 alpha minus 2, and pi 2 is equal to 1 plus 3 alpha. Okay? How do you check that? Well, this is a polynomial in alpha, and so is this. And every polynomial in alpha is a canonical form. Just do the multiplication, simplify, and you will prove this. So to check it is trivial, to find it is not so easy. What is special?
I'm sorry, but you said that all numbers, all prime numbers in Z are not prime in F, except for the divisors of the discriminant.
Yeah, so if a prime number does not divide the discriminant, then it will split into a product of 3. But this one will split into a square. Right,
yes.
right.
And what about 23? I see.
Now you may say, look, I could have done that in any way that I like, but let me tell you something. What is the norm? First of all, this pi p1 is alpha is an algebraic integer, and so 3 alpha minus 2 is an algebraic integer. Anyway, it is in the field. It has a norm. The norm of a number in the field is the product of the Galois conjugates, and you can compute the norm by taking the Galois conjugates and doing some kind of little trace, and you'll find out that the norm of pi 1 and the norm of pi 2 is minus 23. This is exactly what I'm saying, that minus 23 splits as the product of the square pi 1 with pi 2.
Is the Galois group complete group of...
no, it is not. It's not a Galois extension.
It's cyclic.
This extension of degree 3 is not Galois.
Okay, so the Galois group has order 3. Is it?
You can only talk about Galois group of an extension, of a Galois extension.
Okay.
This is the field of degree 3. Okay, so this is a kind of lemma that you get out of this situation.
So what you're saying is that the norm of 7 splits.
Yeah, what I'm saying,
Not 7.
the norm of minus 23, by the way, is not the absolute value, but it is minus 23 to the cube, and the norm is multiplied. Okay, so now let's make something a little bit more interesting.
Can norm be negative?
Yes.
Apparently, yes. Norm is not absolute value, it's the product of all conjugates. So if it's a quadratic extension, then it's it and this complex conjugate, and it's positive. But if it's cubic, so you see, there are all these things that negative numbers are usually excluded from high school books. Especially negative prime numbers. Okay, so let's make this a little bit more interesting. How? Well, so we have Q and we have F, which is Q where we adjoin alpha. Now suppose I adjoin to F also a third root of unity. So zeta sub n, for me it's going to be e to the 2 pi I over n. So this has degree 3, this has degree 2, the total thing has degree 6. Okay. Now, so this is a number field of degree 6. We also learned that in characteristic 0, every number field is generated by an element. How do you find such an element? Okay, let's choose beta to be the following complex number, alpha minus zeta 3. Doesn't matter that I do minus. Okay, this is a specific, a concrete complex number, and that beta satisfies a polynomial equation. So it's a root of the following equation: x to the 6 minus x to the 5th plus x to the 4th minus 2x cubed plus x squared plus 1 is equal to 0. Okay? Is this approximate or exact? It is exactly exact. Okay? If alpha satisfies a cubic equation and zeta 3 satisfies a quadratic equation, the sum of two algebraic numbers is an algebraic number, and there is an algorithm to find the polynomial equation from the polynomial equation of each two. It's a Grosvenor basis algorithm. That you get a polynomial in general of degree 6. That polynomial, if you're unlucky, it will be reducible, but this particular one is not reducible. That's not obvious, but it is true. Believe me. So this E that I wrote is just Q of beta. So every element of V is a polynomial in my beta with rational coefficients of degree at most 5. Uniquely and canonically. Okay, so now I'm going to look at gamma after alpha and beta, which is this particular element. So minus 2 alpha times zeta 6 plus alpha squared. This is an element of E, but it is not just an element of E. In fact, gamma is an algebraic integer, because it is the sum of algebraic integers. And this gamma, okay, it's an algebraic integer, so let me tell you what equation it satisfies. Okay, so gamma satisfies the equation, so a 6-degree equation, x to the 6 minus 10, x to the 5, and 52, x to the 4 minus 188, x cubed plus 421, x squared minus 516x plus 373 is equal to 0, from which we deduce that the norm of gamma is the product of all Galois conjugates is 373. Okay? By the way, gamma is a concrete number, but approximately it is, so I told you that it is 1 minus 2 alpha zeta 6 plus alpha squared, but it is a concrete number. It's 3.382 dot 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 minus 0.532 dot 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 I. Okay, so here's a question. Is 373 prime or not?
So it's smaller.
No, 373 as an integer, is it prime or not?
By definition, it's the product of all roots of that equation.
Yeah, but is 373 a prime number as an integer or not?
Yeah, it is.
It is.
As a...
Is a prime number, as we teach in high school, like minus 23 is a prime number. It is not divisible by anything. So therefore, gamma, I can call it pi of 373, is an algebraic integer of norm 373. So the number, the ideal 373 splits as a product of 6 ideals, and one of them is generated by this gamma, and the others are generated by the Galois conjugates of gamma.
So can you recall what was the definition of gamma?
This is the definition of gamma. Right? Zeta 3. Now you're going to say what is the definition of alpha that I gave you before. Okay? So remember, this gamma is an algebraic integer of prime norm. In fact, Don Zagier told me that primes do not exist. I think I just proved it for you. You have 373, which we all know is a prime, but in this field E, 373 splits into the product of 6 other algebraic integers. One of them is gamma. And in a further extension of E, gamma will split into further. So sure, 373 is divisible by this algebraic integer gamma in a bigger field. So, and since you're allowed to take big and big fields, prime numbers don't exist. They all are divisible by other integers. So adelically, there are no prime numbers. Are we okay with basic number theory? So in case we feel a little uncomfortable, I'm going to switch now into topology and get hopefully get somewhere more familiar territory.
Does gamma generate the same subfield of the same plus beta?
Sorry?
Does gamma...
Yes, because it has degree 6. It has degree 6, yes. Okay. On to the topology. Okay, so most invariants of nodes and links and three manifolds, particular arithmetic interactive invariant, as we have heard, they depend on some data like a Lie group and a root of unity, and they are algebraic integers, as Tang Le told us in great generality, that Tang and Kabirov proved. So therefore, the quantum invariants that we see are cyclotomic integers. And cyclotomic integers are essentially integers up to, you know, a period of n, and because they are integers, they can be categorified. This number alpha that I wrote will have a hard time being categorified because it lives in a non-cyclotomic number field. But I haven't told you yet the connection between this bizarre number alpha that I picked on and knot theory. So now I will tell you how do you get from sort of cyclotomic integer invariants that we know and love, like Reshetikhin-Turaev and Kashaev, to number theory. So I will consider the Kashaev invariant. So in 1993, I believe, Kashaev defined an invariant of a knot K. So K here is a knot. Tang told us luckily a lot about this. Zeta sub n is the nth root of unity. So 1 for every n. Well, odd, but let's not worry about that. And in fact, we can extend it to a function defined at all roots of unity by saying that phi of alpha over b is the Kashayef invariant of b, where we replace zeta sub n by zeta sub n to the a, where a and b is 1. A is co-prime. That is, if you worry how we can replace zeta sub n by a power, given that zeta sub n is a number and therefore satisfies polynomial equations, well, that's exactly what the Galois group does for you. Yeah, it's possible. Okay, we can extend it to a function, and then phi of 1 over n is the Kashayef invariant n. Okay, so that's the Kashayef invariant. Now, but I do want to talk about complete numbers. So you may have seen the definition of the invariant using state sums. I'm going to get into that. So I'm going to give a few examples. Okay, first the figure 8 knot, and the Kashayef invariant is the sum, as Tang also told us, from 0 to infinity, quantum n factorial square, where q is zeta n, and qn is 1 minus q. 1 minus q squared, 1 minus q n. Okay, that's the 4-1 knot. That's not enough. Now let's do this was the 4-1 knot. Now let's do the 5-2 knot. The 5-2 knot, I already drew 5. The 5-2.
I'm sorry. You said that the Kashayef invariant takes values in z of zeta n.
Yes.
But here, a letter Q appears. What's that?
Q is zeta sub n.
I didn't.
It's
okay.
just next
I see.
line.
Okay.
Just for you.
Yes.
So here it's a double sum where k and l are greater than or equal to 0, and k plus l are strictly less than n, minus 1 to the k, q to the l square plus l plus k square over 2 plus k over 2 plus k times l over q l square qk, and q is zeta n. Okay? So for 4-1 it's a single sum, for 5-2 it's a double sum, for 6-3 it's a...
Triple sum.
Yeah, thank you. Not really. The... Right? It has to do with the number of ideal tetrahedra of 6-3. And 6-3 actually, it depends on the triangulation, but it typically uses 4 ideal tetrahedra. The thing is, there are multi-sums. And whether they're in the numerator or in the denominator, it doesn't really matter. You can put them, numerator or denominator, but they look like formulas like that. That's what the Kashayef invariant really is. So now I'm going to tell you about the volume conjecture. So I'm going to tell you 3 conjectures of knot theory. So 3 conjectures. So first is the volume conjecture, due to knot, that says that if you take the log of the absolute value of Kn and you divide by n and you take the limit as n goes to infinity, so if k is a hyperbolic knot, So this is something that you may or may not know. So it means the complement admits a unique, complete metric of curvature -1. Typically all nodes are hyperbolic. You have to be really unlucky not to be hyperbolic. So this limit is the volume of that node complement, which although non-compact is finite volume, divided by 2 pi. Okay, that is the volume conjecture. Then there is some other conjecture. Some people call it the generalized volume, or arithmetic conjecture. It was formulated about the same time by Tangle and ourselves, and also by I can do that finally, and also by Dimofte, group of Lennels and Zagier. Okay, and the conjecture says that there is actually a full asymptotic expansion. So this is going to be e to the c times n to the 3/2, and here a0 plus a1 h bar plus a2 h bar square, and so on, where h bar is a concrete number, 2 pi I over n, and a1, a2, and so on are elements of a number field, not just complex numbers. In fact, this is the trace field of the node. And the same is true for A0, except you need to actually take the square. Okay, that is the generalized volume conjecture. The left-hand side is a sequence of cyclotomic integers. The right-hand side, C, is this constant here, complexified. The volume of a knot is a value of some dilogarithm at algebraic numbers. It is not known if the volume of the figure 8 is an irrational number. That would probably be a field general function.
Can you remind what the trace field is?
Well, I really did not want to talk about, so there's the fundamental group of the knot complement, which is a subgroup of PSL2C. There's actually several people talk about it. So there's the discrete faithful representation, gives you an embedding, so it makes the fundamental group a subgroup PSL2C, and then you look at the number field generated by all traces of all elements. Although the fundamental group is infinite, the traces of the elements, by most of rigidity, they generate a finite number field, and that's called the trace field. The trace field. Trace field. No.
Not correct?
You know what? Here is the thing. Of course, the trace of an element in PSL2C is not well defined, but Q of this is equal to Q of this. The ambiguity with the negative integers is evaporated when you take trace. You don't have to take it. Don't worry. Okay. So, good. That's the generalized volume conjecture. And then there is something else called, in fact, the modularity conjecture. Modularity conjecture of Zagier. That says, well, let's put it this way, that there is an extension not to when Q goes to 1, but when Q goes to any root of unity. So in particular, I told you about this function phi. So suppose we take the function phi and we evaluate it at n over 5n plus 1, which means that we are approaching the 5th root of unity, then you're going to get something like e to the 25c n, 25 being 5 squared, and then there is n to the 3/2, and then here there is a 1/5 0 and a 1/5 comma 1 h bar, and so on, where a 1/5 comma k lie in the trace field adjoining the fifth root of unity. Okay, so if you do the asymptotics of the Kashaev at other roots of unity, you're supposed to get numbers which lie in the extension of the trace field by the root of unity.
So what is in parentheses is something that converges?
No. This is factorial divergent. But the AIs are supposed to exist and supposed to be not invariants.
They don't depend on them.
No, they don't depend on n. I mean, h bar is 2 pi I over n.
Ah.
It's an asymptotic expansion of the sequence, all orders of n. I just wrote h bar because, yes, physics. Okay, oh, and I should say that the trace field of the 5, 2 naught and the minus 237 is the cubic field f from the beginning. So that was the secret relation between the number alpha that I started with.
Actually, I have a question, sorry. Is that an A not squared?
Yeah, that's a square, that's right. And there's something here that involves the fifth root of unity.
I'm sorry, is that number alpha related to both knots here?
That number?
No, alpha. You started with
Oh, yes. It's a generator of the trace field of both nodes, that's right. But these capital A's depend, of course, on the node.
Yes.
And so does the Kashan. It's just that they both are elements of the same number field. You know, that's one thing that both nodes actually share.
Is the picture for this 235 product?
Minus 237. Oh, 5, 2?
No, this one.
Negative, positive, positive. Well, I need
3,
some
6, 7.
1, 2, 3, 4,
No.
5, 6, 7.
The first column.
Oh, too many.
Ah.
I got excited, I guess. Thank you. Minus 237 should be like this. Absolutely.
They have the same volume, right?
Yes, they have the same volume. Other than the fact that they have the same trace field, they also have the same volume, but different asymptotics. Okay, so now I can say something about okay. So complexity. So you might actually have wondered why did I not compute the Reshetik into Rife invariant and give a talk in a conference like that, and I talked about the Kashaev invariant. You might have wondered. Of course, I have to choose a closed three-manifold to compute the Reshetik into Rife invariant, but there is actually a different issue that I want to prove. So, given that so I should say the following. Okay, so the question is, how hard is to compute, say, the Kashaev invariant? The question is, how hard is to compute? Well, it's a number that grows exponentially, so even if you compute it in a second, to just print the output in logarithmic term, it would require linearly many digits. So to the very least of whatever you think of computation, it would require, the best would be linear time, although because of the nature of the formulas, you may think, and the fact that it grows exponentially, you may think that there are exponential time algorithms or maybe sub-exponential or something like that. The truth is actually a little theorem that I have with Donza here, is that Kn is computed in linear time. Linear. Okay, and I'm going to give the proof. Okay, so first of all, we use the fact that Kn is an evaluation of something called the Jones polynomial of K colored by the n-dimensional representation of SL2.
Sorry. Do you mean linear in n?
I mean linear in n.
Not like the number of constant. Okay, I didn't.
I mean it has to depend on n. Okay, so there's the Color-Jones polynomial that Tom told us about, also Aaron, and probably other people too. So that is the starting point. Now you may think that actually computing the Jones polynomial is hard, and actually computing the Color-Jones is even harder. But the Color-Jones polynomial as a sequence of polynomials satisfies a linear recursion. Linear recursion with coefficients, not constant numbers, but coefficients, polynomials in Q and Q to the n. Okay? That is a theorem actually of Tang-Leg, myself. And then if you actually use this linear recursion and you have to actually differentiate it a number of times, you can, if I ask you how fast is to compute the Fibonacci sequence, well, because of the recursion, you only need to remember the last two terms at every time, so it's a linear time computation. For it, okay.
You say polynomial, not linear. Which next step? Linear, yeah. What's the
Linear recursion, yeah. Linear.
But you have to have computed previous two values to know.
Yeah.
What's
Okay.
the order of the recursions? How many terms you must know to compute the
Many. For instance, for the knot 10115, more than 300. But I'm very glad that you asked this question because I want to separate theoretical complexity from practical complexity. So now I will tell you about practical complexity. So, and I'm going to focus about -237. So, complexity, practical. So yes, for every knot you can find a linear recursion for the Color-Jones. But can you actually find a linear recursion for the Color-Jones? For instance, for the Color-Jones of the -237. We can now remove the sum, which I done. Here it is. The answer of the recursion for -237. F of 6 plus n. F is the Color-Jones, so it's a 6th order recursion. With coefficients, the coefficients are polynomials in Q to the n, like Q to the 38, times Q, like Q to the 208. With coefficients, of course, there is a 3. And minus, okay? This one took us about 1 year. This is actually joined with Christophe Chan. And we actually did not prove that it satisfies this recursion. We found a recursion that we conjecture it satisfies, okay? We evaluated the Color-Jones polynomial using mod P reductions for about 1,000 values using fusion formulas and interpolated, and after a lot of work and cluster computations, this is the recursion that I believe satisfies. Now, I have proven a few theorems in my life, and so have you, I'm sure. This is not a proof. This is an experimental computation. I would bet that this computation is more correct than any of the arguments in any of the theorems I have proven. Okay? I bet that this is better, in the sense of consistency and so on, than anything else. Okay? This is how big it is. Okay, this is minus over 7. And by the way, yeah, good.
And for the not 5.2,
Oh, it's half a page. I did not do that. But for the next note, it starts becoming 20 pages, and you know, eventually, the biggest recursion ever computed was for minus 2313, a guess again. Okay, so we take that recursion, and now we go back to the work we've done here. So he pushed me to get that recursion going, and we did it. So now we can talk about numerical computation of the Cosine. Just to give you an idea, for the minus 237, using this recursion, at about color 1500, because we need that kind of high color. The answer is 1.66027 times 10 to the 293. And I want that number to about 800 bits of accuracy. Okay. Oh, now I'm almost actually done with this one. So suppose, numerically, so here and I computed this Cauchy invariant, and at the third root of unity, the asymptotics of it. So we have a numerical table that grows exponentially, and you take the logarithm, and then you do something called the Richardson transform, and so on and so forth. And after some time and after some normalization, I told you we should find out some series which, after you take the exponential term, there is a constant term. And that constant term is, after a little bit of normalization, it is 3.3882 minus 0.532234405 I. Actually, we have got about 50 digits of that number. That's a complex number. It doesn't look very big, right? 3.38. Identify the number. Well, before we actually had the... This is the end of my talk for today.
did you use proof inverter to recognize that?
Before, I'm asking you to identify this number. Huh? Gamma. Yes, it is gamma. Where gamma is an algebraic integer of norm 373 in that number field. The solution to this equation. Okay. So we've done that to various roots of unities, and we actually have some theorems. Unfortunately, I will talk about these theorems as well as about Q series next time, and I will stop.
If not, let us send the speaker again. We need 15 minutes break. So we
I
start
have a request, not a remark. Can you copy me the recursion?
past 11.
Yeah, I want to just to ponder over it, if you don't mind.
He can do that. It's here, and
Yeah.
he can. Yes, it's all.